This video is going to be on section 8.1, which is a single population mean using the normal distribution. So by the end of this chapter, you should be able to calculate and interpret confidence intervals for estimating a population mean and a population proportion. So that's actually 8.1 and 8.3. Interpret the student's t probability distribution as the sample size changes. That'll be in 8.2. Discriminate between problems applying the normal and the student's t distributions, and that's 8.2. Calculate the sample size required to estimate a population mean and a population proportion given a desired confidence level and margin of error. So we're going to work on population means in this video for 8.1, and then population proportions will be in 8.3. So a little introduction on confidence intervals. So we use sample data to make generalizations about an unknown population. And this part of statistics is called inferential statistics. We've done a lot of descriptive statistics, and now we're moving to inferential statistics. So a point estimate is a specific numerical value estimate of a parameter, which is a numerical characteristic of a whole population that can be estimated by a statistic. So remember, we've talked about this before. So parameter has to do with the population, and statistic has to do with the sample. So a point estimate is like 1 point, one number estimate of a parameter. The sample data help us to make an estimate of the population parameter. The point estimate is most likely not the exact value of the population parameter, but a close estimate of it. The best point estimate of the population mean mu is the sample mean x bar. So again, remember, x bar is sample mean, so that's coming from the sample. So that would be an estimate for a population mean, like the true mean of the population. After calculating point estimates, we construct interval estimates called confidence intervals. So a point estimate is just a single number. An interval estimate is a range of numbers. So a confidence interval is a type of estimate, but instead of just being that one number, it's an interval of numbers, a range of numbers. It provides a range of reasonable values in which we expect the population parameter to fall. There's no guarantee that a given confidence interval does capture the parameter, but there's a predictable probability of success. So because of the way your sample works, like you might get that interval and the true population parameters outside of it, but we have a good probability or a predictable probability of success that our true population parameter lies within that interval. So a confidence interval is a random variable, and the population parameter is fixed. The true mean of the population is fixed and doesn't change, but our confidence intervals change depending on our sample. So an example would be if you worked in the marketing department of an entertainment company, you might be interested in the mean number of songs a consumer downloads a month from iTunes. You could conduct a survey and calculate the sample mean x bar and the sample standard deviation s. You would use x bar to estimate the population mean and s to estimate the population standard deviation. The sample mean x bar is the point estimate for the population mean mu. The sample standard deviation s is the point estimate for the population standard deviation sigma. So each of x bar and s is called a statistic because they're coming from the sample. Suppose we don't know the real population mean mu, but we do know the population standard deviation is sigma equals 1 and our sample size is 100. So then we know from the central limit theorem that the standard deviation for our sample mean is s equals sigma divided by the square root of n. So we've seen that before, chapter 7. And in this case, it would be 1 divided by the square root of 100, which is just 10. So 1 over 10 is 0.1. So the empirical rule tells us that in approximately 95% of the samples, the sample mean x bar will be within 2 standard deviations of the population mean mu. So 2 standard deviations is 2 times that s that we just calculated, 0.1, so 0.2. So the sample mean x bar is likely to be within 0.2 units of the true population mean mu. So because X bar is within 0.2 units of mu, which we don't know what it is, mu is likely to be within 0.2 units of X bar in 95% of our samples. So mu is likely to be between X bar minus 0.2 and X bar plus 0.2 in 95% of all the samples that we could take. Suppose that a sample produced a sample mean X bar equals 2. So we can calculate the sample mean. We have the sample. We can calculate the mean, the average of that. But then the unknown population mu is between X bar minus 0.2. So 2 minus 0.2 is 1.8. And X bar plus 0.2. So 2 plus 0.2 is 2.2. So we say that we are 95% confident that the unknown population mean number of songs downloaded from iTunes per month is between 1.8 and 2.2. The 95% confidence interval is 1.8, 2.2. We're often just going to write this statement here, this confidence statement, though you will see me write this confidence interval with those parentheses. Okay, so we were able to calculate the sample mean. We had the standard deviation. So with the central limit theorem, we could calculate the sample standard deviation. And then for 95, we used the empirical rule to know that that would be 2 standard deviations away. So 2 standard deviations times the standard deviation gave us how far away from the sample mean to subtract and add to get the confidence interval. So this is an example that we would do in class. I would ask all the students in the class, how many meals do you eat out per week? We're going to assume that we know the population standard deviation is 3, and we would construct a 95% confidence interval for the true mean number of meals students eat out per week. Because this is the video, I don't have people to sample and ask this question of, but we would collect the data. We would calculate the sample mean. We would use that sigma equals 3 and the number n equals the number of students surveyed to calculate our S, our sample standard deviation. Then we would use that to construct the interval. We would do, if we wanted a 95% confidence interval, we would use 2 for 2 standard deviations away. We would take our sample mean and we would subtract 2 times our S. And then we would add 2 times our S to get our lower number in our interval and our upper number in our interval. And we would say that we are approximately 95% confident that the true mean number of meals that students eat out in a week is between whatever we got here and whatever we got here. We're going to see other examples with numbers. So when we calculate the confidence interval, these are going to have so confidence intervals for some parameters are going to have the form where we take the point estimate, we just saw it with the X bar, the sample mean, minus our margin of error, comma, our point estimate, which again was X bar in the previous example, plus the margin of error. The margin of error depends on our confidence level or percentage of confidence and the standard error of the mean. So we see the term margin of error all the time, and that's where this comes from. So to construct, trying to move my face, a confidence interval for a single unknown population mean mu, where the population standard deviation is known, we need X bar as an estimate for mu, and we need a margin of error. So the margin of error is called the error bound for a population mean. We're going to call it the ABM. And error bound just means like how far, like think about boundaries, how far we can go below and above to get that confidence interval. So our interval, our confidence interval estimate will have the form, the point estimate minus our error bound, comma, the point estimate plus our error bound, or this is what it would look like in sort of formula version. X bar minus the EBM, comma, X bar plus the EBM. So we find that sample mean, we subtract off the margin of error, and we add it on to get our lower and our upper values for our confidence interval. So the confidence level is the percent of confidence intervals that contain the true population parameter when repeated samples are taken. You can choose any confidence level, but usually you choose a level of 90% or higher because you want to be reasonably certain of your conclusions. There's another probability called alpha, which is the probability that the interval does not contain the unknown population parameter. So technically, mathematically, alpha plus our confidence level equals 1. So the steps to construct and interpret the confidence interval are: 1, we're going to calculate the sample mean from the sample data. In section 8.1, we already know the population standard deviation sigma. We're going to find the z-score that corresponds to the confidence level, so that what percentage of the data falls within a certain number of standard deviations. Our previous examples, our z-score was 2 standard deviations away because we were using a 95% confidence interval. We're going to calculate the error bound, the EBM, and use that to construct the confidence interval. The last step is we're going to write a sentence that interprets the estimate in the context of the situation of the problem. We're going to explain what the confidence interval means in the words of the problem. So to find the z-score that corresponds to the confidence level, we need to find the value of z that puts an area equal to the confidence level in decimal form in the middle of the standard normal distribution. So the confidence level CL is the area in the middle of the standard normal distribution. The CL equals 1 minus alpha, so alpha is the area that is split between the two tails. Each of the tails of the normal distribution contains an area equal to alpha divided by 2. The z-score that has an area to the right of alpha divided by 2, we're going to denote by z sub alpha over 2. So here's a picture that represents what this is talking about. So the confidence level, which is in here, is 1 minus alpha. Because it's centered around the mean, alpha is going to be split into these tails, here this unshaded part, and that's going to be alpha divided by 2. So here's our x bar, our mean. This is x bar minus our error bound for the mean, our EBM, and here is x bar plus our EBM. So when our confidence level is 0.95, then alpha equals 0.05, and alpha divided by 2 equals 0.025. So we write z alpha sub alpha over 2 is z sub 0.025. And so the area to the right of z sub 0.025, this is, 2.5%, and the area to the left of that from here over, say, is 1 minus that, or 97.5%. So it's a little bit different because the 95 is in the middle. It's not all on one side or the other. It's in the middle, and so half of the leftover, half of the 0.5 or 5%, is in either tail. So we can calculate that z-score using Excel. And so in this case, z sub alpha over 2 for z equals 0.025 is 1.96. So that kind of makes sense because we were using 2 for 95% confidence, because it's within 2 standard deviations. But that wasn't really considering the exactness of it. So it's 1.96. So to calculate these z-scores, I have this table for you, and these are some standard confidence levels, 99, 95, 90. Here's some lower ones, which we don't tend to use, but they exist. But then I often just use the Excel formula because I just think it's easier. We don't lose, because these are rounded numbers, we lose a little bit of, the precision versus using the formula and referencing the cell in Excel. So it's the norm.inv formula that gives us the value that corresponds to a certain percentage. And so in this case, we're getting a z-score out of it because we're using the standard normal distribution, so a mean of 0 and a standard deviation of 1. And this looks a little complicated, 1 minus the confidence level divided by 2. So this in here, 1 minus CL, that's just alpha. And 1 minus that, so remember, if we, let me see if I can go back. Looking at this picture, right, this part over here is alpha over 2, but we want to the right of that. So we are doing the 1 minus business here. That's what this 1 minus business has to do with. So I'm sorry, I'm not explaining it very well. I think when we start doing the examples, it's going to make more sense. And so I will show you. We do have an Excel sheet that we can reference to work on the examples. So going forward, we're going to come back to that. So when we calculate the EBM, the error-bound formula for an unknown population mean mu, when the population standard deviation sigma is known, is that z-score we just calculated times sigma divided by the square root of n. So that's just S, that's going to be our sample standard deviation, and that is because of the central limit theorem. So you need to remember or write down or take a note of that the error bound for our mean, the EBM, is the z-score we calculate for the specific confidence level times that standard deviation. And then once we have that, we can construct our confidence interval by taking our sample mean, subtracting that number we just got off of it, that's our lower number for our interval, and then adding that number to our sample mean to get the upper number for our confidence interval. And again, here's the picture of it, but we're subtracting off the EBM, which is the z-score correlating to here times the standard deviation, and then adding it on to here to get this number over here. So the final step is writing that interpretation of the information we got, and it should clearly state the confidence level, explain what the population parameter is being, or what population parameter is being estimated, and state the confidence interval, both endpoints. So you would say I shouldn't say something, you're going to say this with the pieces filled in. You estimate with whatever confidence that the true population mean of the number of songs downloaded from iTunes is between whatever number and whatever number. Number of songs, number of inches, whatever, include those appropriate units. All right, so now we're going to do an example and go through all those steps. So suppose the average pizza delivery times are normally distributed with an unknown population mean and a population standard deviation of 6 minutes. A random sample of 28 pizza delivery restaurants is taken and has a sample mean delivery time of 36 minutes. We're going to find a 90% confidence interval estimate for the population mean delivery time. So we have a lot of information in this problem. So the first thing is, what is our X bar? Well, they told us the sample mean delivery time is 36 minutes. The next thing is we want to calculate our z-score for the 90% confidence interval. So now you can go back to that table and look it up. Or if you're working in Excel, let's see, here's example 8.3, which, this is the try at 8.2. I'm just going to walk you through the steps and then we'll get to Excel. So this is just from the table. So then we're going to calculate our EBM. We're going to take that z-score times, this is the sigma from our problem, population standard deviation of 6 minutes, divided by the square root of our sample size, a random sample of 28 pizza delivery restaurants. So that number is approximately 1.134 times 1.645 equals 1.865. So that's our error bound for our mean. That's our margin of error. So we are going to subtract that from our sample mean, and we're going to add that to our sample mean. So 36 minus 1.865 is 34.135, and 36 plus 1.865 is 37.866. So this is our confidence interval right here. We would say that we estimate with 90% confidence that the true population mean time to deliver pizzas is between 34.1 minutes and 37.9 minutes. So I stated the confidence level. the population parameter that we are estimating, and the confidence interval with the appropriate units, minutes in this case. All right, here's example 8.3 that we're going to do in Excel. So the specific absorption rate, the SAR, for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every cell phone emits RF energy. Different phone models have different SAR measures. To receive certification from the Federal Communications Commission, the FCC, for sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. For a sample of 30 phones of different brands, the point estimate of the mean is X bar equals 1.024. Assume that the population standard deviation is sigma equals 0.337. We're going to find a 98% confidence interval for the true population mean of the SARs for cell phones. All right, so when we're doing these solutions, I have everything in the Excel sheet sort of laid out the way I like to do these problems. X bar, that comes from the problem. They told us that. So over in Excel, we're going to type in that X bar, which was 1.024. Now we're going to calculate the Z-score for the 98th percentile, or the 98% confidence level. So we're going to use that norm.inv formula. And remember, the probability goes in first. So if our confidence level is 98, that means alpha is 2. And really, it's 0.02. We're going to divide that by 2. Okay? And we're going to do 1 minus that. So you don't have to put it in parentheses. I don't think. Sometimes I like to, because I feel like then I know for sure which way we're doing the multiplications, additions, and subtractions. So again, 1 minus, this part here is that 1 minus the CL. So the CL is 0.98, 1 minus that is 0.02, divided by 2. Now our mean for these problems, we're using the standard normal distribution, so the mean is always 0, and the standard deviation is always 1 to find the Z-score. So 2.32635. If you look at the table, you'll see, actually, I don't know if we had 98. We might have 99 and 95. All right, so the next thing we want to figure out is our S value, or sigma divided by the square root of n. So I did that. That's this piece in here. Okay, so sigma, we're told, is 0.337, and our sample size is 30. So we're going to do equals 0.337 divided by the square root of 30. So that gives us our S value. And now the EBM is equal to the Z-score times that S value. And see, I like to use my Excel cell references to help me do my problem. So my EBM is 0.14313. That's my error bound for my mean. That's my margin of error. I'm going to subtract that from the mean and add it to the mean to get my confidence interval. So here's the 0.143. You can see the math done out here. And so subtract it and add it to get our confidence interval. In Excel, the upper bound for my confidence level is going to be X bar plus my EBM. It's the bigger number. And the lower bound is going to be X bar minus my EBM. I did it upper bound, lower bound. If you were doing this without my little boxes in there, you can do it in either order. But my confidence level, my confidence interval is going to be between 0.88 and 1.17. As you can see, I did more than that, decimal places. So what we say now is that we can say with 98% confidence, the true population mean SAR will be between 0.88 and 1.2 watts per kilogram. So I stated the confidence level, the population parameter being estimated, the confidence interval using the appropriate units. So this is a challenging topic, but if you go step by step slowly, you can get the answer. You just have to make sure that you take it slowly and go in order. So here's another example. It's try it 8.3. It's the same idea, but we have a different sample of 20 phones this time. So we have a different sample mean, different point estimate of X bar equals 0.94. We keep the same population standard deviation. We are also changing our confidence interval here for the true population mean of the SARs for cell phones. So, solution, we're still going to type into Excel our X bar. This time it was 0.940. We're going to calculate our z-score for 93%. So norm.inv 1 minus, in parentheses, what is 100 minus 93? It's 7. As a decimal, it's 0.07. Divide that by 2. 1 minus alpha over 2. We always use the mean of 0 and the standard deviation of 1 because we're talking about getting a z-score, so it's the standard normal distribution. So we get 1.812. Our next step, calculate our EBM. In Excel, I gave you a spot to figure out your S value. So it's going to be sigma, which in this problem was 0.337, divided by the square root of our sample size. Our sample size changed. In this problem, it's 20. So the square root of 20. The EBM is always going to be that z-score times our S value, 0.13654. Now we subtract it and we add it to get our confidence interval. So our interval upper bound is going to be equal to our mean plus our EBM. Our lower bound is going to be our mean minus the EBM. So now we have our two values. So in this case, it's 0.8035, comma 1.0765. And we can say with 93% confidence that the true population mean SAR will be between 0.80 and 1.1 watts per kilogram. So see, this confidence interval is different than the last one because we had a different sample. So a different sample will give us a different sample mean, will give us a different S value, which will give us a different EBM. And so those things together will give us a different confidence interval. So the confidence interval in example 8.3 was 0.8809, is less than mu, is less than 1.67. So we're saying that the true population mean is between those numbers. And then in try at 8.3, we were saying mu was between 0.8035 and 1.0765. These intervals are different for several reasons, like I just said. Different samples, the samples were different sizes, the intervals were calculated for different levels of confidence. So even though the intervals are different, they don't yield conflicting information. So in general, if everything else stays the same, a 98% confidence interval is wider than the 93% confidence interval because the z-score is bigger. A smaller sample size will give a bigger EBM, which will give a wider interval. Changing the confidence level increases the error bound, making the confidence interval wider. Decreasing the confidence level decreases the error bound, making the confidence interval narrower. So here are two pictures illustrating that. So for a 90% confidence interval, maybe you can see that the purple here seems to be a little bit narrower than the green here, which is 95. So making that confidence level bigger, increasing it, makes the confidence interval wider. So increasing the sample size causes the error bound to decrease, making the confidence interval narrower. Decreasing the sample size causes the error bound to increase, making the confidence interval wider. This is because the EBM formula divides the standard deviation sigma by the square root of the sample size. So the larger the sample size, the smaller this number becomes, so the smaller the EBM becomes, and vice versa. If this is smaller, this gets bigger, so this whole thing gets bigger. So another example, try at 8.5. A new random sample of 50 pizza delivery restaurants is taken and has a sample mean delivery time of 36 minutes and a standard deviation of 6 minutes. We're going to find the new 90% confidence interval estimate for the population mean delivery time. So X bar is 36. So over in Excel, X bar is 36. We're going to find our z-score for 90%. So remember norm.inv. And do 1 minus. So 90%, 100 minus 90 is 10. So as a decimal, that's 0.1. We're going to divide that by 2, comma. Our mean is 0. Our standard deviation is 1. So that is our z-score. We're going to figure out our sample standard deviation. So we know that the population standard deviation is 6, and we have a sample of 50 pizza restaurants. So this is going to be equal to, sigma was 6 divided by the square root of 50. Yep. And then we are going to multiply, and here you can see 0.8485. EBM is going to be equal to our z-score times our S value, 1.3957. And now we're going to add that to our mean for our upper bound, and we are going to subtract it from our mean for our lower bound. So we can estimate with 90% confidence that the true population mean time to deliver pizzas is between 34.6 minutes and 37.4 minutes. Our old confidence interval was 34, that our mean was between 34.1 and 37.9. So this, because the confidence interval, it was just that other things changed, not the confidence level. Confidence level was the same, but the interval got narrower in this case. So if we know the confidence level, we can work backwards to find either the error bound or the sample mean. To find the error bound, from the upper value of our interval, we can subtract the sample mean. If we, or from the upper value of the interval, subtract the lower value. So big minus small, divide that by 2. Either one of those are ways to find the error bound. So depending on what you know, if you don't know the sample mean, you would do this method. If you know the sample mean, you could just subtract it from the upper value for the interval. And then to find the sample mean, it's very similar. If we know the error bound, we can subtract it from the upper value of the confidence interval, or we can average the upper and lower endpoints of the confidence interval. So if we add the upper level plus the lower level and divide by 2, that will tell us the midpoint, which would be the sample mean. So these are the 2 ways to find the error bound and the 2 ways to find the sample mean if you have the confidence interval. So suppose we know that a confidence interval is 42.12, 47.88. We're going to find the error bound and the sample mean. So to find the error bound, we don't know the sample mean, so we're going to subtract those 2 values. Upper minus lower and divide by 2. That gives us 2.88. You can do this in Excel. You would just, in parentheses, take the upper one, 47.88, and then you would subtract off 42.12, close your parentheses and divide by 2. That gives you your error bound of 2.88. And then to find the sample mean, since we don't know the error bound, I mean, we do, we just found it. But if we didn't, we would add those 2 values together. So again, we're going to use parentheses, 47.88, but plus this time, 42.12, close our parentheses and divide by 2. And that gives us our sample mean of 45. If we had calculated this, we could just subtract it from 47.88. That would also give us 45. And so that's how we find those. So if researchers desire a specific margin of error, they can use the error-bound formula to calculate the required sample size. Calculating sample size n is this fun formula here. It's not as bad as it looks. It's the z-score squared times the standard deviation of the population squared divided by the error-bound at the mean squared. Now multiply the z-score times sigma, divide by EBM, square the whole thing. Because everything's being squared, you can do it the multiplication and division first and then square. We get this by solving for n in the EBM formula. So a researcher planning a study who wants a specified confidence level and error bound can use this formula to calculate the minimum size of the sample needed for the study. So the population standard deviation for the height of a high school basketball players is 3 inches. If we want to be 95% confident that the sample mean height is within 1 inch of the true population mean height, how many randomly selected students must we survey? So we're going to use this formula. What is the z-score for 95%? You can either, use the table, do it in Excel. We're going to take that number and square it. We're going to multiply that by the standard deviation, which in this case is 3 squared, and divide by, see how it says that within 1 inch? So that's our error bound of our mean. And that's why this is in the bottom and squared. So like I said, you can square each one and then do the multiplication and division, or you can do the multiplication and division and then square the whole thing. But we get n equals 34.57. You're going to round up because this is the minimum number we need for our survey. We can't have parts of basketball players, so we would round up to 35. That way we would be 95% confident that we would be within 1 inch. So I'm just going to show you in Excel really quickly how you could do that. So in here, like I said, you could in parentheses do norm.inv to find your z-score, but we're just going to type it in right now. It's 1.96 times our standard deviation of 3 divided by our error bound. So we were within 1 inch, and then you can square the whole thing. And that gives us our 34.57, which we would round up. But again, if you needed to, you could always do the norm.inv formula. We want it to be 95% confident, so 1 minus in parentheses, 0.05 divided by 2. Our mean is 0, our standard deviation is 1. So that's where the 1.96 comes from. So you could always, instead of putting in the 1.96, you could reference this cell here. Same answer. So anyway, different ways to do it, but I just wanted you to see how to do that. So that's the end of the video for 8.1 on the single population mean, where we know the standard deviation.